let's look into this chapter 3. Still in chapter 3, we are looking into the RLC circuit. So in the RLC circuit, now we are looking into the step response of parallel RLC. So in the step response parallel RLC, we can see that it is very similar, lebih kurang sama dengan source free parallel RLC circuit, but the difference is only it appears there will be one DC source, at least one DC source appear in the circuit. And after we choose KCL, Kirchhoff's current law, to do the circuit analysis, the second order expression should be written in terms of the current, or also you can use a voltage equation. Okay, so this is the second order expression for the current, d square I dt square plus 1 over RC di dt. Okay, so it will have the same coefficient, which is important to determine the frequency parameter. As for the solution for this equation, we should have two components. One is the transient response, Vt, and the other one should be the steady state response. So this is the total solution, current, steady state current, and also the transient response. And this is again very similar to what we have done in the source free case. So we have overdamped case, critically damped case, and underdamped case. But the steady state response is now we are looking for the final value where your steady state is I infinity, which now in the circuit it should be equals to IS. The value of A1 and A2 should be obtained based on the initial condition of I naught and the I naught dt. So if you look into this circuit by KCL, actually we are having the equation of C dV dt. Okay, and then for the KCL part, the KCL, we start from the equation of current. So current in the capacitor should be C dV dt. And the time goes by, we perform the time derivative and we got the homogeneous ODE of Vt, which is independent of the current source. So you will have the equation of dV dt, but somehow from the homogeneous, now you can always choose, or you try to solve the equation using inhomogeneous ODE. Okay, so by choosing this one in the inhomogeneous ODE, so actually based on this for step response RLC circuit, we can always choose either homogeneous or inhomogeneous ODE. Okay, so this actually changed the unknown to the inductor current. Just now we are using the capacitor voltage. Okay, so from here you can always obtain the equation of d square I dt squared plus 1 over RT dIL dt plus IL dt. Okay, so the next we can do the equation in terms of to solve your A1 and A2. So we will need the inductor current, which cannot change abruptly by using initial inductor current, and we also need the capacitor voltage initial value. Okay, and from here we have the VL naught dt equals to L di dt. So we are going to use the I naught equals to V naught over L for the initial condition. In terms of the general solution, this is the response which we apply the nature and also the steady state or the force response. So from here, you will have a very similar format of for the responses, but at the but there will be additional of I force or I steady state. Okay, as for example, let's look into this equation. So let's say you have 24 milliamp and you have 25 nanofarad, and there will be one switch over here. So the question, what is your IL? Okay, so for this case, we apply the alpha equals to 1 over 2 RC. It gives you 32 kilohertz, and we find the omega naught. It gives you 40 kilohertz, and then you should compare it. This is the same step as what we have done in the source-free circuit. Okay, so comparing these two, we will have your alpha is less than omega naught. So alpha less than omega naught, it gives you an underdamped case. Okay, solving the parameter, the complete solution is in the form of IS plus exponent minus alpha times alpha t times B1 cos omega t plus B2 sin omega t, where your omega d is actually taken from the omega naught squared minus alpha squared, and you find the square root. Okay, so we have 24 kilohertz. By taking this one, we can see that you have two constants, B1 and B2. So how to solve this is by using the initial condition. The initial condition that we want to use is I naught, I0, and the I0 D naught, which will be equals to your V naught divided by BL. Okay, so from here, your I naught should be equals to 0, and in this case, the second equation also it gives you 0. So you have two equations. Solving these two, we get B1 is minus 24 and B2 is minus 32 milliampere. Okay, so you solve this now. So if you try to do the simulation should look like this. This is your current, inductor current. By using the equation that you have. This is a 24 milliamp. Okay, and this one, you can see that there will be overshooting at the beginning of your time response. Okay, so that's all for the example.